Okay. Very good afternoon, everybody. Welcome at this fest. I have to perhaps even warn you, this is the first fest ever that we're going to record. So behave, of course, in your questions today. Anyway, today I would like to announce you one of our Fanny researchers from the geochemistry department. He originally did his studies, his bachelor studies at the University of San Diego State in California, and afterwards moved to Berkeley in California to do his master's and actually also his PhD in civil engineering, civil and environmental engineering university there. He specialized more in later in X-ray, on synchrotrons, and mineralogy. And in general, Scott, I can say that, yeah, I think water quality could also, he's also involved in low general scope. Today he's going to take us along in his research of the last years on arsenic pollution in groundwater. Please give him a very warm welcome. Kees van Genuchten.
I'm going to time myself here, make sure I don't run out of time. Well, I want to start by thanking the organizers for letting me have the opportunity to talk about what I'm doing. I actually had a lot of fun putting the slides together for the talk because I don't have a whole lot of opportunities to spend a lot of time on the background of the project. And I think the background, at least from the socioeconomic perspective, is really interesting, in addition to the technical and chemical perspectives. But I spend a lot less time talking about the socioeconomic parts at scientific conferences. So I'm really enthusiastic about preparing and presenting this talk. And
Which I'll put on.
oh yeah, that's
This is recorded as well.
there you go.
We did it on purpose.
Okay. Right, so I've split the talk into 4 parts. The first 25%, I'm going to be discussing the background of the project, so explaining the motivation, talking about the arsenic crisis in general, and then giving a little bit of the socioeconomic approach to designing technologies. And that's where I'll introduce the technology that I'm working on, which is called ion electrocoagulation. And I'll also be describing the current challenges with electrocoagulation for removing arsenic from groundwater used for drinking, and then maybe why mixed valent iron oxides can be the answer. Then the next part of the talk is going to be the first scientific part, where I'm going to identify the conditions, so how to form mixed valent iron oxides by iron electrocoagulation. The next part is the second scientific part of the talk, where I'll be discussing how arsenic interacts with mixed valent iron oxides generated by iron electrocoagulation. And then, if there's time and the audience is still awake, I'm going to try to give some updates, some recent updates with field work that we've done that relates to extended operation of this technology in the field. This part I might cut a little bit short depending on time, but we'll see how that works. Okay, so I'm going to get started by thanking the co-authors of the work. So Peter, Kroll, and Thilo. Peter used to be at Utrecht. Thilo is still here in the audience. And then in Copenhagen, I got some help from Susan Stipp and Knut Didriksen, and that's going to be for parts 2 and 3 of the talk. I did a lot of the work at synchrotron, one in Grenoble, ESRF, and one at Stanford, SSRL. And of course, I'd like to acknowledge the funding body, NWO. This is part of my Benny grant. So for part 4, I got to acknowledge Simon Müller, who did most of the work for part 4, at least for the lab-based part. And then the field work, there's been a lot of people that helped. But for the purposes of this talk, Shiva Bandaru from UC Berkeley and Abhishek Roy from Jadavpur University, which is a university in Kolkata in West Bengal, India, that we have some pretty strong collaborations with. Okay, so I mean, there's plenty of things to say about naturally occurring arsenic contamination. Really, it's a worldwide concern. We have naturally occurring arsenic in groundwaters in the Netherlands, but we also have pretty efficient centralized water treatment here, where it happens to be one of the biggest problems with respect to human health impacts. It's in the Bengal Basin, so the entire country of Bangladesh and northeast India. And there's a number of reasons why that is. One is that it has high naturally occurring arsenic concentrations, so about 300 to 1,000 micrograms per liter, whereas in the Netherlands, you wouldn't find it more than maybe around 50, I'd say. But also, there's very little infrastructure here. So most of the communities where arsenic most of the arsenic affected communities live in really decentralized areas. So places where you don't have piped water coming to your house. And you're really limited in what kinds of technologies that you can design that are going to be able to function sustainably in communities like this. So arsenic in general is kind of a nefarious problem because it's tasteless, colorless, odorless, and it's got a high latency period, meaning if you drink contaminated surface water with pathogens, you might get sick the next day. But if you're drinking water with arsenic in it, you won't see signs for a long period of time, months, if not a year, and then you start to see the signs of it. So you have to build a lot of trust with the community. That's going to be a theme in the talk, is the relationships that you build with people that live in arsenic-affected regions. Chronic exposure to arsenic leads to, you initially get these lesions on the palms of your hands, which are painful, but it ultimately leads to cancer and death. So over 100 million people drink arsenic-contaminated water daily, and almost half live in rural South Asia, so Bangladesh and northeast India. So I'm going to spend a little bit of time on this slide because I want to talk a little bit about what kinds of technologies are going to be sustainable in communities like this. And when I say sustainable, I am mostly referring to economically sustainable. And so this is a big problem because a lot of technologies are typically designed in labs that have very little interaction with the community where the end users live. And so the technologies that are developed, they're not designed to be embedded in the community, and you end up having in West Bengal just graveyards of technologies that are just completely disused. Because once the aid organization or the research institution that developed them, once they leave, there's no incentive to keep the technology maintained. And so we've worked with a lot of public health specialists and socioeconomic experts to think about what kinds of design constraints that the technology needs to fit into. So one of them obviously needs to remove arsenic, needs to be effective at technically removing arsenic. It needs to produce very little waste. It needs to be, I think the most important thing is that everything that goes into the technology needs to be locally available and locally affordable. That's critical because that cuts down on supply chain and that eliminates costs and complexity. So it's got to be a low-tech solution. What we've developed is called iron electrocoagulation, and the way that it works is we take pieces of iron. So iron is ubiquitous, it's very easy to find. One of our first prototypes was using iron nails, but now we use sheets of iron, and we insert these pieces of iron into pumped groundwater. And then we attach a small current to it, small electric current to it. And that corrodes the piece of iron the same way that it would naturally, but it does it at a faster rate. And this is another major theme of the talk, is that rate that it corrodes is directly proportional to the magnitude of the applied current by Faraday's law. So if you change the applied current, you can change the rate of iron 2 production. So we apply a small electric current to it. The iron 2 dissolves into the iron metal dissolves into iron 2, which is in solution, and then iron 2 is oxidized by dissolved oxygen to produce particulate iron 3 oxides. Arsenic is removed by binding to the surface of the iron 3 oxides, and so to remove arsenic, you can just let the iron oxides settle by gravity, or you can filter them. Let's see, any other parts of this? I think that's good for now. This is a very simplified schematic. In the lab, this is what it looks like. You can see the pieces of iron here, and then this yellow, brownish, orangish rust iron oxides. So it's important to remember that Arsenic removal occurs not on the electrode surface, but in suspension. Okay, so just to give you a little tour of the kinds of upscaling of the reactors that we've been doing. So this is typically what we do in the lab still. We played around with a kind of a 30-liter fish tank prototype for a little bit. These bubbles are air. Then we upscaled it to 100 liters, and this we produced in the lab, but then shipped to West Bengal and tested local groundwater with it. Then we upscaled it to 600-liter per batch reactor, and the stage that we're at now is a 2,000-liter batch reactor. And so if this is operated the whole day, it can treat about 10,000 liters per day. And so when I talk about the field work, it's going to be with this reactor. Okay, so one of the most important ideas about designing technologies is thinking about how you're going to implement them. And for a number of socioeconomic reasons, we target schools. And what I'm going to show you now is where the site of where this plant is currently operating and where this one used to be. And so here you can see Bengal Basin right here. When you zoom in, there's Kolkata, and this is West Bengal. The school is in Dapdapi, which is there. And when I go do field work, I usually stay on campus at Jadavpur University. So to get from Jadavpur to the field site, to the school, take a train, and it gets pretty hectic on the train. But it's once you get to the village or to the train stop where the village is, it's very nice. It's very rural, it's decentralized, very green, peaceful. And you take this bike from the train station to the school. This is an aerial image of the school just to give you an idea of what it looks like. Here's the front of the school. There's me and Shiva. And this is the side of the school. And actually where the plant is located is right here in this building. And there's me, and incidentally, I am wearing the same shirt. I think I show up with the same shirt many times in this talk. And there's Cal. But this is where the plant is located, directly adjacent to the school. And this is just one shot of inside the school. Okay, so why do we target schools as sites to implement the technology? So we do that for a number of reasons. One is that if you form a good relationship with the headmaster, that facilitates having the teachers teach the children about arsenic. So the level of misinformation in some of these communities is very high. And so the idea is that if the teachers teach the kids about arsenic, or the kids will teach their parents about arsenic, and then the education in the community will increase. The other reason is that it fits within this kind of business plan or the implementation model that we have, where the school council is willing to pay a small amount of money, but is still willing to pay money per liter of treated water, and that money goes to the local business that's now operating the system. And the local business is this person and this person. But then the community also participates in treating the water, and that's really what we're after, is we want the community to take ownership over the technology. If there's a financial reason, like there's an economic reason here, that is even more motivation for the community to take ownership over the technology and really care for it, rather than abandoning it. So those are all the socioeconomic reasons why this technology seems to be a good solution. My expertise is really in the chemistry of what's happening, but if there's questions on the socioeconomics, I can try to answer those. So the way that we have it implemented is pretty simple. We take pumped groundwater and it goes into an electrolysis tank. That's where we add the iron 2 via iron electrolysis. That is pumped into a coagulation tank where we add a chemical coagulant, and that's sent into a settling tank. We have the settled solids here, and then we have the treated water. In pictures, this is what the electrolysis tanks look like. If you look down bird's eye view, you see the steel plates here. There's Shiva and I, different shirt this time. Here's the settling tank, and then this right here is where this treated water is sent after settling. Then that's piped around here, and this is where the kids can interact with the safe water kiosk. And the business actually gave the kids these cards, and they have a little chip in there. And they can use it one time per day for 1 liter of water. Now, when I went last December, one of the interesting things that happened, which I was not suspecting at all, is that the business that operates the system now has taken it to a place where we didn't think it was going to go, because they started to sell the excess water that they treated to the community. And in fact, that is what I'm showing here is people came walking up to this part, and the business fashioned a little spigot here, and it's on an automatic, it's automated to spit out 5 liters of water. And so I was really, it was very satisfying to see all sorts of people, young, old, men, women, coming at in the day to this part of the plant and paying for water. And so there's a willingness to pay for this water from the community. That was really surprising for me. I don't think it's very common that this happens. All right, so if things seem to be going well, what's the problem? That's summarized here, that the precipitates that we generate, the iron 3 oxides that we generate, they are extremely small, nanoscale, and that means that they're very difficult to remove from the treated water at low cost, and that's summarized here, where after 24 hours of gravitational settling, the water is still turbid, and that's where arsenic is. And so that forces us to use a chemical coagulant and a coagulation tank. And this adds cost, complexity, it adds extra size to the footprint of the system, and we want to eliminate that supply chain. So as I mentioned before, one of the things to always remember with this talk is that by changing the way that we apply the current, we can change the rate at which we add iron 2, or which iron 2 is produced. And that's really important, because controlling the current, therefore, gives us the ability to manipulate redox reactions involving iron. And so what we can do pretty easily with this system is just by increasing the current, increasing the iron production rate, we can generate iron oxides that have structural iron 2. And that's what this is, green rust and magnetite. These are mixed valent iron 2,3 oxides. And these mixed valent iron oxides have very interesting properties. So the iron 3 oxides, as I mentioned before, they have a really small particle size, and they're not the best for settling by gravity. These ones have some unique properties that will facilitate particle separation. For example, green rust, you can see here it's a hexagon. It's got this hexagonal crystallite, but it's much, much larger than our nanoscale iron 3 oxides that we produce. And that means that green rust settles very quickly, and you don't need to add a chemical coagulant. Green rust also has reactive edge sites on the particle surfaces, and so it can scavenge arsenic in the same way that iron 3 oxides would. Magnetite is interesting for a couple of reasons. Of course, it's magnetic, and so that can facilitate low-cost separation with a low-strength magnetic field. But it also, in the structure, it has tetrahedral iron sites. And that's really important because arsenic 5 is tetrahedrally coordinated, arsenic 3 is pyramidally coordinated, but it's very similar shapes. And so there's been previous work that suggests that arsenic can actually substitute for these tetrahedral iron sites in magnetite, leading to very stable sorption configurations where arsenic actually is part of the particle rather than just binding to the surface. Okay, so that's the idea. If we know how to generate these mixed valent iron oxides, we'll be able to eliminate this step, which eliminates the supply chain associated with the coagulant, and hopefully makes the whole system more efficient. But to get to that stage where we're going to implement the iron 2,3 oxides, we have to first learn how to produce them. Then we have to figure out how arsenic interacts with the different mixed valent iron oxides. And these are the scientific parts of the talk that I'm going to be speaking about. The work still to do is to determine the effects of groundwater ions, so calcium, magnesium, phosphorus, silica. How do those change the structure of the iron oxide? How does that change how arsenic is taken up? And of course, what happens to precipitated arsenic with time? You can see that it completely changes color. So what does that mean for arsenic uptake? All right, so that's part one, and I'm just going to check my time here. It's not bad. Okay. So now hopefully we're on the same page about how the technology is designed, how we intend to implement it. Now I'm going to get into some of the molecular scale details about how to produce the iron 2,3 oxides. So the objective here is to determine what kinds of, determine the electrochemical controls on the iron 2,3 oxides that are produced by iron electrocoagulation. So basically, how does changing the current lead to these different iron oxides? And so to address this objective, we looked at two systems. One I call the controlled system, where we control the dissolved oxygen concentration. at 0.1, 0.3, and 3 milligrams per liter, and we did that by using gas mixtures of nitrogen gas and air. And the other system that we looked at I called the uncontrolled system, where dissolved oxygen was just left to float in response to the iron production rate. So here we set it at 3 milligrams per liter, and then we just let it go. If you're because of lack of time, I'm not going to talk about the control system at all. One, because it's not very representative of how we do things in the field. In the field, we're open to the atmosphere. And two, the data didn't look as interesting as in the uncontrolled system. But if you're curious, I would encourage you to read about it if you'd like in our recent paper. So most of the data that I show will be from the uncontrolled system. All right, so the approach here, uncontrolled system, we generate 3 millimoles of total iron 2 by iron electrocoagulation, and we looked at different pHs from 7 to 10. Different background electrolytes, we looked at sodium chloride and carbonate, 10 millimolar each. And then for the uncontrolled system, which is what I'll be showing, we also changed the iron production rate. Again, by changing the current, we can change the rate at which iron 2 is produced. And so we looked at 30 to 100 micromoles of iron 2 per minute, and that corresponds to a total electrolysis time of 10 to 100 minutes. All right, so we basically generated the oxide and then took that directly into a glove box where we filtered it in the glove box. We measured aqueous iron, but more importantly, we characterized the solids by X-ray absorption spectroscopy and X-ray diffraction and some pair distribution function analysis. But for this talk, I'm only going to be showing the X-ray absorption spectra. And just so I know we're all caught up on what XAS is, it's a powerful method of probing the local coordination environment about elements that you can choose, meaning that this is an element-specific technique. And this is really important for arsenic, because if you have a dilute species in a mixture, it's very difficult to probe using standard X-ray methods. So X-ray absorption spectroscopy, by virtue of it being element-specific, is really the method of choice for characterizing dilute species. But it also does not require long-range orders. So X-ray diffraction relies on a periodic lattice of atoms, but X-ray absorption spectroscopy does not require that. So you can use it to characterize nanoscale material. And the kind of information gives, we can get the average oxidation state and then the local bonding environment around iron or arsenic. And that means the number of atoms that are bound to the element of interest and the interatomic distance. Okay, so we characterize the samples by X-ray absorption spectroscopy. Okay, so straight to the results. This is the uncontrolled system again, and here these results are for the chloride solution. So what I'm plotting is the dissolved oxygen concentration on the y-axis as a function of the total iron dosed at different iron production rates. So at the lowest iron production rate, the dissolved oxygen actually increases due to the flux of O2 from the atmosphere, and it ends higher than it started. As we increase the iron production rate, iron 2 consumes dissolved oxygen, and at the highest iron production rate, the final dissolved oxygen concentration is below 0.1. So that's for pH 7. pH 10, we see very similar trend. As we increase the iron production rate, we decrease the dissolved oxygen concentration. Okay, so here are our EXAF spectra for the samples that are produced at the end of electrolysis. We can see that there's some nice oscillations there, but how do we interpret this? So I won't get too detailed. We can talk about this after the talk if interested. But we treat the whole data set as a whole, and we first pick out, we do principal component analysis to pick out the principal components. And that's what I'm plotting here. So we found 4 components, could reproduce the entire data set. And the first component looked very similar to green rust. So this is a green rust reference spectrum. The second component looked very similar to magnetite. The third component looked very similar to lepidocrosite. And the fourth component was similar to a nanocrystalline iron 3 oxide, similar to ferrohydrite. I'm going to call it hydrospheric oxide for this talk. Okay, so then we take these principal components and we do linear combinations of them to fit our sample spectra. And that's what we get. So as we increase the iron production rate from 30 micromoles of iron per minute to 300, we see that we generate iron 3 oxides, but those we generate iron 3 oxides at the low iron production rate, and then magnetite starts to form at the high iron production rate. So you're getting mixed valent iron oxides as the dissolved oxygen concentration decreases. So for pH 10, we see very similar trends, but instead of generating lepidocrosite at the low iron production rate, we're getting hydrospheric oxide at the low iron production rate. But magnetite seems to be forming both at pH 7 and 10. So what are the conclusions from this? Well, the most pure magnetite forms when the dissolved oxygen concentration gets below 0.1 milligrams per liter, and to get there required the highest iron production rate. Solution pH was much more important to the iron 3 oxides that formed. We didn't see a big difference in the iron 2,3 oxides that formed, and we didn't see any evidence for chloride green rest. Okay, we can do that whole treatment that we did for the chloride solution for the carbonate solution, and this is the results that we get. So actually very similar trends. As we increase the iron production rate, we transition from iron 3 oxides to purely green rust. And that's true for both pH 7 and pH 10. So the major conclusions from all of this: the most pure mixed valent iron oxides formed at the highest iron production rate, and that's more or less what we'd expect. And there's a competition between the flux of oxygen coming in and the iron production rate as controlled by the applied current. And so the iron 2,3 hydroxides require the rate of iron 2 production to be higher than the flux of oxygen coming in. And so we can ensure that by increasing the applied current, or just by cutting off oxygen to the system. So we can put a lid on the tank. All right, but the most important part for this talk is that now we have a recipe for producing these mixed valent iron oxides. Okay, so that's in part 2, and my time is still okay, great. So now that we know how to form these mixed valent iron oxides, the next part of the talk is going to be discussing how arsenic interacts with them. But before I get into that, I wanted to point I wanted to discuss a little bit the standards of arsenic in drinking water, because I think this is pretty relevant to the next part of the talk. So I'm going to start up here at 1,000 micrograms per liter, because that's more or less the maximum for naturally occurring arsenic concentrations. Anything far beyond this, 10,000 micrograms per liter, that's going to be from anthropogenic sources. If you bring that down to 50 micrograms per liter, that's the standard for arsenic in drinking water in India and Bangladesh. Bring that down to 25, that's the standard for China in rural areas. And you bring that down to 10 micrograms per liter, that's kind of the global standard. So that's the World Health Organization, the US, many countries in Europe, Australia, and then urban areas of China. However, there has been some recent research that suggests even at concentrations of arsenic lower than 10 micrograms per liter, you still have incidents of health impacts. And this is really, in getting to know some of my colleagues at KWR, it's been very interesting to see what they've done with this. So Arzan Ahmad, Patrick Vanderwens, they really spearheaded this idea that Dutch drinking water companies should target 1 microgram per liter in treated water. And in fact, there is an agreement amongst the drinking water companies to target 1 microgram per liter. And this is kind of a controversial idea, particularly outside of the Netherlands. But I think that as this information becomes more public, other countries are going to do the same. This is the Netherlands 1 microgram per liter standard I don't think any other country has targeted that. So clearly, there are technologies that are required to get arsenic to below 1 microgram per liter. Okay, so again, taking the recipe for producing these mixed valent iron oxides, the next step is to determine directly how compare directly how each iron oxide interacts with arsenic. So basically, we just generated the green rust, magnetite, and iron 3 oxides in the presence of either arsenic 3 or arsenic 5. And we looked at a range of arsenic 3 and arsenic 5 concentrations from about 200 micrograms per liter all the way up to 11,000 micrograms per liter. And that corresponds to an arsenic to iron mole percent of 0.1 to 5. And we also looked at 2 pHs, 7.5 and 9. Now, similar to the last part of the talk, we basically generated the iron oxide, and then with arsenic 3 or arsenic 5 at the beginning, and then transferred that suspension directly into the glove box, where we filtered it. And the residual arsenic, so the arsenic remaining after removing the particles, we measured using hydride generation AAS, and that's actually a pretty important part of this part of the talk, because the arsenic concentrations in some of the samples were very low, and it required this method. Okay, and the arsenic speciation at the end of generating the particles by electrocoagulation, the arsenic speciation in the filtered solids, we characterized using X-ray absorption spectroscopy. And there's just a few more data points where we took the solids and then exposed them to different solutions to see how likely it was arsenic would be knocked off the particle. Okay, so what I'm plotting here is the residual arsenic concentration. This is a log-log scale, but the arsenic concentration remaining after removing the particles as a function of the initial arsenic concentration. And I have two gray lines. I don't know if you can see, that didn't show up, but two gray horizontal lines that correspond to the 10 microgram per liter WHO limit, and then this 1 microgram per liter target. Okay, so generating green rust, we can see that for most of the arsenic concentrations that you would find in the environment, green rust can get below 10 micrograms per liter. We get slightly better removal at pH 7.5 as opposed to pH 9. For the iron 3 oxides, we're able to get below the WHO limit almost every time. And again, we see this trend of better removal at pH 7.5 relative to 9. For magnetite, this is very interesting. Magnetite doesn't matter what the initial arsenic concentration is, it doesn't matter the pH, we're able to get below 1 microgram per liter every single time. And again, we did this with arsenic 3 as well. I'm not going to show too much data, but magnetite was also able to get below 1 microgram per liter for the initial arsenic 3 concentrations that at least were lower than 2,000 micrograms per liter. Okay, so what can explain this really exceptional removal of arsenic from magnetite? For that answer, we turn to our X-ray absorption spectra. What I'm showing here is the extended X-ray absorption fine structure spectra for the green rust samples and the iron 3 precipitate samples. And generally, you can see that they're fairly similar, and they're very smooth. You see smooth oscillations. When you compare that to the magnetite data, magnetite, you see some beats, you see some interferences in the EXAF spectra. And that's already suggesting that the local coordination environment of arsenic in the magnetite sample is different than the other oxides. Okay, so how do we interpret that? Well, we can Fourier transform the EXAF spectrum to get peaks that correspond to atomic pairs at a given radial distance. And so these peaks are what's going to be able, we can use the amplitude and the width and the position of these peaks to get meaningful structural information about how arsenic is coordinated. So for arsenic 5, the first peak is going to be arsenic-oxygen pairs. Oxygen is the closest atom next to arsenic in arsenate. And then you have a peak due to arsenic-iron pairs. And this one is really important if we're going to assign sorption configurations. So what we can do is model the position, amplitude, and breadth of these peaks to get structural information, and that's what we've done here. So the coordination number, so the number of oxygen atoms surrounding arsenic in our modeling, the fit-derived coordination number was around 4 at a distance of 1.7 angstroms, which is exactly what we would expect for arsenic 5. The second shell, we found a coordination number of arsenic iron to be around 2 and at a distance of 3.4 angstroms. And that's consistent with this binuclear corner sharing configuration. Similarly, for the arsenic 3 oxides, the model was very similar to green rust. The coordination number for the first shell was 4 oxygen atoms at 1.7 angstroms, which is consistent with arsenate in tetrahedral coordination. And then we have the same kind of binuclear corner sharing configuration. And that's based on a coordination number of 2 and a distance of 3.36. Now, let's look at magnetite. So not only do we see a much larger second shell peak, but the peak is shifted to longer interatomic distances. And so when we fit this, the first shell of oxygen atoms is very similar, coordination number 4, interatomic distance 1.7. But then the second shell is much different than the other iron oxides. So we can actually fit 2 sets of arsenic iron pads in this one peak. So the first one is positioned at 3.46 angstroms, and the second one is at 3.65 angstroms. And the coordination number is much, much higher. It's not 2, it's 8 and 6. So arsenic in a magnetite sample is surrounded by iron atoms. So how do we interpret that? What's going on? We take a look at the magnetite structure, and we zoom in on part of the surface, and we get rid of some of the atoms that are confusing, and then we're going to rotate this so that we're looking down on it, and we're going to remove the tetrahedra. There. If we just go by the crystal structure of magnetite, this tetrahedral iron site is surrounded by a number of iron atoms at 3.45 angstroms. So there's 10 in this kind of configuration. If we add the tetrahedral iron for magnetite, they're situated at 3.6 angstroms away from this tetrahedral site, and there's 4 of them. Now, if we pretend that arsenic substitutes perfectly for that tetrahedron here, the arsenic iron distance will again be 3.45, and the second iron arsenic distance will be 3.6. So this is, in theory, what we'd expect if arsenic substitutes perfectly for that tetrahedral site. If we compare that to our fit-derived interatomic distances, they're very similar. 3.45 angstroms in theory, and then the fit-derived was 3.46. The second arsenic iron path 3.6 and 3.65, so very similar. The coordination numbers are a little bit different, but still these interatomic distances are compelling evidence to support the idea that arsenic is substituting for the tetrahedral iron site. And that's really important because we're forming multi-nuclear complexes where arsenic is bound to at least in 3 locations, but it's surrounded by iron atoms. And if you just look at arsenic bound to the surface of magnetite, the second shell peak is much lower. Okay, so why is that important? Well, these different sorption configurations from green rust to iron-free precipitates to magnetite, magnetite is a multi-nuclear complex. And that likely influences the thermodynamic equilibria between arsenic in solution and arsenic on the solid phase. And so by virtue of these different sorption configurations, that can explain the differences that we see in the macroscopic uptake of arsenic. So magnetite, you can get below 1 microgram per liter every time, and you have arsenic in these tetrahedral sites. Okay, but that's not all. Arsenic is also less likely to be remobilized. So what I'm showing here is arsenic remobilized, or arsenic knocked off the particle for ferrohydrate at pH 14, and in the presence of phosphate, it's much higher fraction than for magnetite. So coming back to our initial objective, to try to determine which iron oxide is best for arsenic removal, for sure it's magnetite, but it's not just based on the residual arsenic concentration. It's also based on the sludge stability and the ease of particle separation. But we also have to think about treatment time and the power required to generate these iron oxides, as well as the long-term efficiency. So how does generating these iron oxides, these different iron oxides, change over long periods of generating them, months, if not years? All right, so those were the 2 parts of the scientific talk. But there's still some work to be done with this project. So the first is, I mentioned before, building in complexity. So it's adding phosphorus, silica, calcium, magnesium, see how that impacts both the structure of the oxide and how arsenic is taken up. And then also tracking iron and arsenic speciation over time, because these mixed valent iron oxides are metastable. Okay, and the last part. Okay, I think I can zoom through this. Right, so now we're at the final piece of the puzzle, which is, I'm going to talk a little bit about some recent work that we did in the field with respect to understanding how iron electrocoagulation, how this technology operates over longer extended periods. Some of the practical challenges with that and some unexpected benefits of generating mixed valent iron oxides. Okay, so these pictures are just to get your mind back thinking about the field again. So as I mentioned before, it seems to be working well, but there's an interesting problem that we noticed. So one of the things about working in the field is it's quite difficult to collect robust measurements consistently. And so really the only long-term measurements that we have of the field data is arsenic removal and how much charge was passed. But if you use those two measurements and compare the efficiency of arsenic removal in the lab versus in the field, you see that the field treatment, you actually have to pass a lot more current to remove the same amount of arsenic. And so one of the reasons hypothesized for that in this paper is that when you operate an electrocoagulation system over several months, what can happen is that the electrochemically generated iron actually doesn't make it into solution over time. It starts to accumulate on the surface. And that surface layer grows at the expense of iron 2 into suspension. And so what we want in this system is to generate iron 2 into solution so it can form the iron oxide. We don't want it to form a precipitate on the electrode surface because just by mass balance, very little arsenic is removed on the electrode surface. Okay, so one of the reasons why we went into the field is to kind of test this hypothesis. Does the surface layer actually impact arsenic removal performance? So what we did is we measured as many performance indicators as we could. Arsenic, phosphorus, silica, manganese, the total voltage that's required to pass current, dissolved oxygen, pH, etc. We measured all of these things before removing the electrodes, cleaning the electrodes, putting them back in the tank, and then measured them again. And so what we wanted to understand is, does cleaning the electrode, if there's a surface layer, does removing the surface layer actually improve efficiency? And I'm going to see if I can play this. Okay, so this is us removing the electrical connections from the electrolysis tank and then taking out all of the electrodes. So it's not a small task. Let's say that. Anyways, okay, so that worked. I'm happy. Now let's see if I can, yes. Okay, so that was the approach, remove the electrodes, and we can very clearly see that the surface of the electrodes has been substantially modified by some really interesting looking iron oxide surface layers. And the heterogeneity of these surface layers is really amazing. This scale is 1 centimeter here, it's a little piece of tape I put on there. But you can see that you don't see very much bare iron metal anymore. So what we did after that is we got an angle grinder and fit it with a wire brush and basically just the whole thing and got dust everywhere. But it seems to work pretty well. You can see before cleaning it looks like this. After cleaning, you see some bare metal down here. And this black stuff is actually magnetite. Okay, so what did that cleaning actually do? Well, it improved the amount of iron that got transported into solution the next run. So after 60 minutes of electrolysis, before cleaning, we got about 12 milligrams per liter. After cleaning, we almost tripled that at about 30 milligrams per liter of iron. And that means that we got much more removal of arsenic, much more removal of phosphate, more removal of silica, more removal of manganese. So in fact, yes, removing the surface layer helps, but it costs a lot of effort, a lot of time, and that's money. So is there something else that we can do? And to answer that question, I turn to Simon Mueller, a master's student who graduated, I don't know, several months back, and posed that question for him. And so what he did is he tried to reproduce exactly how the field system operated, but just did it in the lab. So he reproduced the electrode material. We actually brought home a piece of the metal that's used in the field. He reproduced the iron production rate, the charge dosage rate, the total iron produced, the total charge passed. Similar solution chemistry, used the synthetic groundwater, and then also reproduced the same cycles of electrolysis and air drying as what's used in the field. But he also changed some important electrochemical parameters. So he played with the solution chemistry, he took out the oxyanions, he took out the bivalent cations, and instead of generating iron 3 oxides, he produced the mixed valent ones. So he changed the iron production rate, he increased it. So what did he find? Sure enough, at the low iron production rate, the way that the system is operating in the field, we get a steady decrease over repeated operating cycles in the total amount of iron that's produced, or that makes it into suspension. So after 35 cycles of operation, about 2.5 months, we're only getting about 60% of what we would expect based on Faraday's law. Not only that, the surface of these electrodes starts to accumulate an iron oxide surface layer. And to the tune of about 2 milligrams of surface layer per centimeter squared. Okay, so this again is the low iron production rate. If we increase the iron production rate and produce mixed valent iron oxides, all of a sudden we're able to sustain a little bit higher of the iron 2 production efficiency. So at the high iron production rate of 83 micromoles per minute and above, we're able to sustain about 90% of what we'd expect based on Faraday's law. And we don't see this quite a similar surface layer on the electrodes. In fact, we get about 10 times less iron accumulated on the electrode at the high iron production rate. So why does that happen? We came up with 2 reasons. The first is that as you increase the current, you're also increasing the interface potential. And so you have a highly positive polarized anode here. And it's ejecting iron 2. And iron 2 is positively charged at circumneutral pH, so you're going to get some electrostatic repulsion. The other is that as you generate iron 2 quickly, the flux of dissolved oxygen, say, into this control volume is going to be smaller than the rate of iron 2 production. So you're going to be, you could envision an area near the electrode where there's a local gradient of oxygen, where there's very little oxygen near the electrode, and that means that iron cannot form an iron oxide precipitate and then attach to the electrode. Okay, to sum up everything, why is generating mixed valent iron oxides? Why can that be the answer? Well, the first reason is that it facilitates low-cost particle separation. The second is that, especially for magnetite, you get very effective arsenic scavenging. And then the third is that we don't see this drop in the production of iron over extended operating cycles. Okay, so work to be done. I've already described this, and this is work to be done on my project in the next year. But what I'm most interested in the far future, well, maybe in like a year and a half to 2 years, is thinking about how to sustainably manage this arsenic-laden waste that we produce. So I didn't talk at all about the oxides, what we do with them after they've done their job in the treatment. But we are left with this, and arsenic is bound on there. So one thing that we do currently is we put it in concrete to use as a building material. But I don't necessarily think that's the best idea. What I'd really like to try to do is develop a circular economy for this material. So try to extract as many resources as we can from the solids and detoxify everything, and hopefully generate something that has value. So if you would like to talk about those ideas later, I will be around. Finally, thank you for following along. I don't know if I set the record of slides, but 172. Let's see what I did on time. Yeah, not bad time.
Thank you, guys. Well, let's see if we can set the records on questions. May I try? Otherwise, I have to come up with some myself. It's usually a good sign that it was clear. Well, I'll try one myself. You've been studying this one at a particular, applying it at a particular location.
Yep.
Do you expect any differences yet when you apply it, for example, at another location, or the quality of groundwater curves?
Definitely, yeah. So that's one of the major motivations for testing, for building in complexity the solutions that I'm looking at. But I expect that different groundwater chemistry will certainly alter a lot of the processes that happen. So there's many processes: iron 2 oxidation kinetics, the formation of the oxide, competition for surfaces with arsenic. But there's more to it than that, because when you want to, I think finding locations where this kind of technology is going to be suitable, especially in rural communities of South Asia, you have to find the right community. So, I mean, of course, a community that doesn't suffer from arsenic poisoning is not necessarily going to be so interested in this. But there needs to be, you have to build relationships with the community too. So kind of, copying and pasting this technology in different communities just like that it's not as easy as that. You have to build trust, you have to build relationships, and that's a really fundamental part.
So not only chemical aspect, but also the social economic aspect.
Absolutely, absolutely. But there are quite a lot of plans of implementing different plants that are similar in design in different communities. So we have one that's going to happen in the Philippines relatively soon, but nothing that is so developed as to be distributing water yet.
Let's start at the back and then go for it. Happy.
Have you been able to get the people of the community interested in the research?
Yeah, that's a great question. I think that they are definitely very interested in what we're doing. Trying to discuss the chemistry of what happens, that's difficult. But I used to, when I up until actually like a year and a half ago, when I went into the communities and did some like maintenance on the system, I really tried to be invisible. And that's because I didn't want people to see that I was there, didn't want people to think that there's a problem with anything. But we work a lot with an economics professor at Genuchten University, and she was telling me that that's not the right approach. You want to make yourself known because that builds trust. That really increases the understanding that the community has of what you're doing. They want to know that you care about what's happening, and so you really want to make yourself known. And as far as discussing things personally, I don't speak Bengali, but I've discussed things with the local operators as much as I could. But there's definitely an interest, but the level of education isn't very high.
Because the reason why I ask is that that's obviously a way to improve the public engagement in a project like that. And so I'm curious if there's ways to you can actually design projects that are associated to this, that are actually accessible to the communities.
Yeah, I think that's one of the hopes of working so closely with the headmaster of the school is that we did, I mean this was years ago, and I wasn't really involved in this, but we had a few people working on kind of outreach in a way, designing pamphlets for the school children that didn't have words. It was mostly images and pictures, but working with the local teachers to develop strategies of explaining what's happening with arsenic to the children. But yeah, I think that's a critical component of this, and that's why I don't think that copying and pasting this system in every community is going to work, because it's such an important part of building up the education and trust.
That was neighbor.
I was wondering whether this is also a problem for other types of food like rice. Is it?
Yes. Yeah. Oof. That's a long discussion there. So, absolutely. There's been a lot of work on trying to develop strategies to maybe play a little bit with the chemistry of the sediments that rice is growing, because of course you have a lot of uptake of arsenic into rice, and it depends on where you are on the planet. And I just went to a conference a couple months ago about this, and I wish I could give you more informed information. But I know that there's a definite correlation between cadmium and arsenic in rice. And so if you play with the chemistry a little bit, say you amend the soil with some iron oxides or another kind of arsenic scavenging mineral, and try to encourage arsenic binding to the sediment, you get a spike in cadmium. But yeah, there's a lot of work that's done both on a fundamental perspective, like seeing how rice is taken up, seeing how arsenic is taken up into the rice shoot, and also remediation strategies for that. So I mean, I haven't. This technology would not be geared to that segment of the population, but it's something that I'm very interested in.
Hi, really enjoyed your talk. Regarding the iron sheets that you have,
Yes.
is there any? Have you heard of magnetic water treatment? I've heard that gets rid of scaling. I don't know if you've.
Yeah. Okay. So. I think with that part of the project, I'm a relatively inexperienced person. So just getting into the electrochemical reactions that happen on the electrode surface, I wish I could speak a little bit more informed about that. But I have heard a bit about the magnetic separation. One interesting thing that I found in the last year is that if you have, so one of the things we do in the field is we reverse the polarity of the electrodes. If you do not do that, then you have a very clear and gigantic calcite layer that forms on the cathode. And so we can actually get a lot of calcium removal if we don't change the polarity of the electrodes. But as far as preventing the iron oxide growth on the electrode using some magnetic technologies, I'm interested to maybe hear your thoughts.
Just something I came across. Can I also ask one?
Sure.
What do people know, like the health effects? People in the community recognize that there's issues long term that they will have from drinking.
Yeah, I mean, in this community, for sure, they know that there are effects. I would be really interested in talking to some epidemiologists to see if we can see, because of this system, if there actually is a decrease in, like, arsenic in urine or something like that. That would be really incredible. But I think those kinds of studies are also very difficult because so much comes into play. But I'm quite positive that most of the community is very concerned with arsenic. But as far as like documenting any change in health because of the system, we haven't done anything like that.
That's a question in front of you, and then one at the side.
Thank you for a very interesting presentation. Also nice to see my colleague Aslan pass by, so you know about the more high-tech approaches that
Sure.
he's going on.
Actually, I just heard. Oh, sorry, I didn't mean to.
Just as an introduction. Yeah. You mentioned in the beginning that the system you had installed was capable of treating 10,000 liters per hour. Per day.
Yeah.
Sorry, per day. I'm missing it from the rest of your presentation. What the mass removal rates are, because I imagine it also depends on kinetics, and with these lower oxygen concentrations that you need to get the magnetite produced.
Yeah.
Can you comment on the mass removal rates?
Yeah. So there's a couple of things here. You mentioned the kinetics. So I didn't show much arsenic-3 data, but the kinetics for arsenic-3 oxidation when you generate magnetite green rust are much lower than for iron-3 oxides. So certainly you get less arsenic-3 oxidation when you generate the iron oxides very quickly. If you generate it slowly, I'd say my data suggests that all of the arsenic is oxidized. Okay, so that's one thing. As far as the total operation of the system, what we do now is we've done a number of experiments in the way that the system is set up now in batch mode. There's been a lot of talk of doing things in a continuous flow reactor, but we haven't quite taken that idea to the next step. And one of the reasons why is because in some of the smaller prototyping stages, it didn't work that well. And it could be like mechanical engineering people weren't doing the right job, but I think that it would be that we've gotten that comment a lot is can you make of like a continuously produced reactor. And at this stage, I would say that we probably could, but we haven't yet. I don't know if that answers your question. Okay, sorry.
Then we go to the final question.
Thank you. Not being an expert on the technical aspects, I'll concentrate my question on the socio-economic part. What is the installation that you have in that village school? What is the operating cost of that? And then as a takeoff from that, since there are some entrepreneurs who are making money out of it, does that make a positive economic impact so that those people can reproduce the system and have motivation to reproduce the system elsewhere?
Yep. Okay, so I think the answer to the first question is it changes because as you start to operate the system over longer periods of time, you require more electricity to pass the same amount of current. You require more power to pass the same amount of current. So at any particular time, I'm not really sure how much it costs to operate, but I am very certain that just based on the amount of water that is the business is selling, that it is less than 3 rupees per 5 liters, something like that. The second answer to the second question is, while I think that this is a really good example, and I do think it is making, so far it seems to be economically viable. I don't think that it would be a good idea to implement a similar system in a community without having gone through a lot of groundwork to figure out what kinds of arsenic concentrations you have, what the groundwater chemistry is like, what the community, who the community are. I think it would be great if we could take this example and then put it in different communities because it's so effective. But I don't think that the cost of operating it, or the money that is gained by selling the water is so much more than the cost that it would be so easy to do. Does that make sense?
I think it does. Okay, so I want to thank you very much. And let's go to the basics.